Hi, I'm Michael Howard. I'm going to talk about some common, all too common security coding issues. I want to point out this is not an exhaustive list of every single possible potential security vulnerability. It's just some of the more common ones and some of the more important principles that you should understand when it comes to building software. There are really only two types of security issues you need to worry yourself with. The first one is input trust issues, and the second one is everything else. This sounds kind of like a flippant comment, but if you look at the majority of really nasty bugs on the internet, they're mainly because you trusted some inputs on the way in. Now, don't get me wrong. For many types of customers, other types of vulnerabilities are extremely important. They've got nothing to do with input trust whatsoever. But for the ones that really grab the headlines and really affect a lot of customers, are ones relating to input trust. And really the mantra that we use around here is all input is evil until proven otherwise. And this is a really important point. If good guys can give you good data, bad guys can give you bad data too. So the classic examples here are buffer overruns, where you expect data to be this big and you actually get data that's this big instead. Or a SQL injection attack, where you expect some specific text and you get some text that actually changes the syntax or the semantics of the SQL query. Now, for those of you that know 1 equals 1, sorry, no SQL injection attacks, you'll notice I have 1 equals 1 down there. Now, I'm not asking you to remember 1 equals 1 for the reasons you think. Just keep an eye on that, and I'll explain why I'm asking you to remember 1 equals 1 shortly. And last, you've got cross-site scripting bugs, which are where you expect some text, and you actually have text that's mingled in with HTML and script. There are other kinds of injection attacks as well, like XML injection attacks and LDAP injection attacks. And they're all basically the same kind of attack. So you expect some well-structured data, and the bad guy gives you something else that you weren't expecting. So we're going to focus, first of all, on buffer overruns. Buffer overruns have been known about for a long time, and the analogy that people use is actually a really bad analogy. The analogy is to take an 8 ounce or 12 ounce, let's say an 8 ounce cup, and fill it with 12 ounces of water, and the 4 ounces goes all over the place, has to go somewhere else. The analogy is really bad. In fact, I really don't like security analogies, but I will continue the analogy in a little bit more of an accurate manner. Take the cup, seat it on your laptop keyboard, and then pour 12 ounces of water into the 8 ounce cup. The fact that it overflows the cup is a nuisance, but the real problem is the way it then makes your laptop go snap, crackle, pop. The problem is when the data overflows, the water, in this case the water overflows, it's the ensuing damage that happens. So for example, in the case of a buffer overrun, you overflow a buffer and you start smacking other sensitive data in memory. And that's where the problems really start. C and C++ are by far the most common victims of buffer overruns. There have been buffer overruns in other languages, but they tend not to be in the language itself. They tend to be in the runtime environment, which, guess what, is usually written in C or C++. The other thing to bear in mind is that the vast majority of buffer overruns, the buffer actually comes in as data and then is executed as code. So you've got this problem of data being treated as code. The most common, well actually the most well-known buffer overrun, and by far the easiest to exploit, is the stack-based buffer overrun. So here you'll see a layout of a stack from low memory on the left to high memory on the right. And here you've got a function called func, and you have a 128-byte buffer, and then above that you have other stuff that's not buffers. So for example, you've got a scalar value, a class, and a function pointer. Then after that, you have the function's return address. So when the function returns, it needs to know where to go back to. And there's usually 2 registers that are pushed on the stack, the EBP and the EIP register. The EBP register is usually is optional, but in many cases, both are pushed on the stack. Or where to continue the execution on is pushed on the stack. And then finally, you have the arguments. And so in this case, you have a pointer to a char or series of chars and an integer. What's interesting is that this memory layout can contain information that determines the flow of execution. So for example, exception handlers, function pointers, virtual methods. The function return address is another example of something that determines execution flow. And because of that, the attackers will target these. Because if they can corrupt one of these values, they can actually change the flow of execution. And that's the whole point of a buffer overrun, is to change the flow of execution from what would be the normal flow of execution to an execution flow determined by the attacker. Now here is one of the most important skills that any developer should learn. what does the bad guy control? If the bad guy controls nothing whatsoever, you probably got a bug. If the bad guy controls a lot, you probably have a security bug. And in this example, the bad guy controls this buffer and what it's pointing to. And there's a problem here, because if you look at the last function call, there's a call to stir copy, which keeps copying until it bumps into a trailing null. Well, the problem is the bad guy controls that buffer, so he can determine exactly where the trailing null goes. So what happens is bad things start to happen if the data pointed to, that's controlled by the bad guy, is longer than the destination buffer. Because what happens is stir copy keeps copying until it bumps into the null. Well, if the null is beyond the length of the buffer, then it just keeps whacking stuff in memory until finally it bumps into a trailing null. In the meantime, you may have corrupted all sorts of things in memory. For example, you may have corrupted the function return address. So when the function returns, it takes those values off the stack and continues execution at that point. Well, if I can change that value, I can make it start to the start of my buffer. And my buffer could contain malicious assembly language, known as the payload. At that point, the function func returns, but it returns to the start of my payload and continues execution. And at that point, the bad guy is running the code of his bidding. And at that point, you are owned, which means that the computer is no longer yours. The bad guy is running the code of his bidding, and it's no longer under your control. This is really bad if the process is running in elevated identity, such as system or root, because now the malicious code is also running in system or in root. For a long time, people focused on stack-based buffer overruns and not on the other major class of memory, which is heap-based buffer overruns. Turns out heap-based buffer overruns are also highly exploitable, but they're just different to stack-based buffer overruns. To understand how heap-based buffer overruns work, you've got to understand the basic layout of the heap. The heap is just memory, and you can allocate and deallocate dynamic memory from the heap. And every single block that you allocate is called a heap block. At the start of every heap block is some metadata. Most importantly, there is a link to the prior block and to the next block. It's a doubly linked list. So when you free a block, the heap manager has to coalesce the heap to make sure that it's all stitched up correctly. And it does that by taking the metadata out of the heap block, finding out where the prior block is, where the next block is, and then linking those two blocks together. It's called coalescing the heap. Well, the problem is, in that metadata, there are two values. One is, they're both basically the same, an address and a value to write to that address. There's two of those, which means that on heap free, the value D1 is written at the address pointed to by A1, and D2 is written to the address pointed to by A2. Because of that, the bad guy will target that metadata. Because on heap free, what will happen is I can overflow the first heap block, smack the metadata of the next heap block. So when that heap block is freed, I can start writing arbitrary D words in memory. And they may think, well, okay, who cares? Well, you can start whacking things like variables. So a variable may be a Boolean value that says, no, you're not allowed access. Well, I can patch it to say, yes, I am. Or you can start whacking function pointers to point to some exploit payload instead. So this is a very important class of vulnerability. So moving stuff from the stack to the heap does not fix buffer overruns whatsoever. Here's a real simple example of a buffer overrun. This was found in Microsoft SQL Server instance resolution. It was bulletin number MS020339. And again, it's always really important to understand what the bad guy controls. In this case, the bad guy controls this buffer, RGP receive buff, and the bad guy controls it because it's read directly off the network. If you look at the function call, it's a call to receive from, which is a UDP read off the internet. So it reads no more than max received message bytes into that buffer. If you look at the buffer definition, it's max received message bytes in size, which is 256 bytes. So there's no buffer overrun there. This call to receive from is listening on port 1434, which, unless you have a firewall in place, is probably going to be the internet. So it reads no more than 256 bytes into that buffer. Then further down, we call it this function SSRP enum, passing in the second character onwards to this function. And we treat that second character onwards as a null terminated string. So RGP receive buff comes straight off the network. We're now going to treat the second character onwards as a null terminated string. The bad guy controls it. The bad guy can determine exactly where the trailing null goes. And so in this case, we would receive no more than 256 bytes off the network, then write it into this other buffer, SZReg version, using sprintf. It's a totally unbounded function call. It's not bounded by any source or destination buffer size. And so what it keeps doing is just looking at SZ inst name, looking for the trailing null, which the bad guy controls, and the net effect is you can overflow this buffer. This buffer is only 128 bytes in size, and we're receiving no more than 256 off the network. This is a buffer overrun. This is what led to the slammer worm. So what's interesting is a lot of people say, well, don't use sprintf, don't use strcpy, don't use strcat. You should use the n functions instead, like snprintf, strncopy, strncat. At Microsoft, we ban those for new code. In fact, we talk about those in the SDL book. One of the chapters at the end lists the SDL banned functions. And sprintf and strcopy and strcat are in there, but so are snprintf and strncopy and strncat. They're in the banned functions too. And the reason is they're very hard to get wrong. Very hard to get right. Here's some very simple examples. Here's the first example. Okay, we're calling strncopy. It must be secure. So what's wrong with the code? Well, the problem here is we're allocating the size of a pointer. We're not allocating the length of the string. So we're allocating on a 32-bit CPU only 4 bytes and copying no more than 50 bytes into a 4-byte buffer. Buffer overrun. We may be calling strncopy, but it's completely insecure. Or another doozy. So you're calling strncopy again, copying no more than max, which is the buffer size, into the buffer. Well, there's a problem there too. If the length of the PSE source, the length of the incoming buffer, is exactly max or longer than max, strncopy does not null terminate the string. This is just a time bomb waiting to go off. Or another example is, again, must be secure, we're calling strncopy. Well, the problem here is we're passing in the constraining length is the length of the incoming buffer that the bad guy controls. So yeah, you're calling strncopy, but the buffer size is wrong. You're saying don't copy more than the source buffer size. So you decide, okay, well, we're going to call strncopy, we're going to call it securely, and we're just going to put the trailing null in there. Well, we've seen this happen a couple of times too, where you force the trailing null. Well, you just whacked element number 51, not element 50. Arrays start at 0, not 1 in C and C++. Or what about this one? You call strncopy and strncat. You know, this possibly could be secure. Well, the problem here is that actually there's a bug in strncopy, but the big one is actually in strncat. The problem here is that max minus 1 in the last argument to strncat is not the size of the buffer, it's how much is left. So again, we've got the wrong buffer size. Next, we'll call snprintf and we'll say don't copy any more than whatever the destination buffer size is. Well, we're calling strlen here on an uninitialized buffer. So if the trailing null is 2k away, snprintf here will copy no more than 2k into a 50-byte buffer, which is again a buffer overrun. This is not a buffer overrun, but it's an example of an insecure coding technique that is still particular to strncopy and strncat. And the problem here is we're not checking that the incoming buffer, P, is not null. If you're passing null here to strncopy and strncat, your app will just crash. Now, this may not be a massive issue for some apps, but for servers, this is a big issue. Your email server just went down, or your web server just went down. I mean, this is a big deal. So the real lesson here is, even if you're using the n functions, strncopy, strncat, and so on, you can't disengage your brain. They don't make strncopy, strncat, and snprintf, and so on don't make you miraculously clever. They don't. You've still got to do some thinking. In fact, we actually don't like these functions at all at Microsoft now, and part of SDL we ban them because they're just so hard to get right. The next class of attack is integer arithmetic attacks. This is really a catch-all for three kinds of issues: overflow, underflow, signed versus unsigned, and truncation. The problem isn't really the integer arithmetic. The problem is the buffer overrun that comes swiftly in behind. That's the real problem. So let me give you an example here. Let's say you've got this function that concatenates two buffers. And you got buff1, buff2 of len1, len2. And he's saying very early on that if the length of the two incoming buffers when added together is greater than the destination buffer size, then return -1. Well, that's fine. But what happens if len1 and len2 are these two values? If you add these two numbers together, they wrap around on a 32-bit CPU, they wrap around to 2 to the 32nd. So these two numbers actually add up to 255. Then you end up copying a little bit more than 255 bytes into the buffer. In fact, you end up copying over 4 gigs into this buffer. What's interesting about this is your app will not copy 4 gigs. The moment your app walks off the end of the last page, the CPU and the OS will intervene and say, where do you think you're going, and shut the application down. The problem there is it may have corrupted stuff in memory that's to do with handling the wind down of the corrupted process. And so if you could corrupt that data, you could actually have your code run as part of the wind down process of the application, which again is a bad thing. Another example, we've seen this quite a bit too, is where people write their own custom memory allocators. What I mean by that is they take some block size or some size that they want to allocate and they round it up to the next blocks and the next block size. Well, the problem is, in this example, if you want to allocate essentially 4 gigs, this code will allocate 0 bytes. Now, you may think, well, why don't you just ban allocating 0 bytes? Personally, I don't think I have ever knowingly allocated 0 bytes. Ever. Turns out some people do it as a common pattern. They allocate 0 bytes and then reallocate later. Personally, I don't like that, but we found that it's actually very, very common across the industry. So you can't just ban 0 byte allocations. But it's another example of an integer overflow in this case, where you're rounding up to the next block size. The next block size just happens to be 0 bytes. Also be very wary of managed code calling unmanaged code. Here you've got an example of some C# code that is checking that some incoming buffer sizes and values are all correct, and then you call a naked mem copy in C or C++. Well, in managed code, unless you stipulate otherwise, all integer arithmetic is against signed integers. So you could have a value here of input count being -1 and get past all your managed code checks, but in unmanaged code, the input count value is actually treated as 4 gigs. So it gets past all your size constraint checks, but then it's treated differently by unmanaged code. So be very careful of calling unmanaged code from managed code, where you do a lot of range checks in the managed code first. You really should be doing the range checks in the unmanaged code. So here you've got like an impedance mismatch, where one environment is treating integers in one way, and another environment is treating integers in a completely different way. So how on earth do you fix these problems? There's many ways. One is to search for risky functions and determine where the data came from. I mean, if you've got a call to stir copy, where did the data come from? Did it come from somewhere I trust? What does the bad guy control? Does the bad guy control this? If the answer is yes, you've got to fix the code. If the answer is no, perhaps you don't have to fix the code. The other way of fixing it is just to use these better libraries. Use things like StirSafe, which is available on MSDN and in Visual Studio, or the Safe CRT. One thing that the Visual Studio team at Microsoft have been working on is a replacement for the C runtime libraries like stircopy, stircat, stir-encopy, stir-encat, and so on. You have this thing called the Safe CRT, which is available as part of Visual Studio 2005, which is, as I mentioned, are just drop-in replacements for stircopy, stircat, and so on. And in fact, if you compile your code today with Visual Studio 2005, we'll show you that stircopy and stircat and all these other evil functions are deprecated. And if you double-click, we'll show you a function that you can actually use instead. Or use SDL, the standard template library. I mean, if you're using strings and you're like an admin console or something, just use the string class. Don't go using native raw buffers. Go using the string class instead, and let the buffer manipulation be taken away from you to a much better implementation. Fuzz tests. Sean talked about fuzz testing, which is another way of finding these bugs as part of the development, as part of the testing process. So I won't go into that in any more detail. Sean talked about that. Next, I want to talk about some other defenses that we have. So we have the thing called the GS flag. GS actually adds runtime checks to the code, and it's added by the Microsoft compiler. And we can detect certain kinds of stack-based buffer overruns at runtime. And in fact, we're into our fourth generation now of the GS code. And that's why we mandate at Microsoft that it must always be using the latest versions of the compilers, because we add more defenses to the compiled code. NX, otherwise known as DEP, Data Execution Protection, requires certain support from CPUs. So, for example, one of the machines that I have at home is an AMD 64FX machine. I'm running 32-bit Windows XP Service Pack 2, and it can detect if some data comes in and I try to run that as code. So a good example is the WMF flaw. I actually wrote a malformed WMF file and viewed it in the shell. It wouldn't work. And the reason is that the CPU recognized that that's data, not code. And then when the malicious, the bug actually tries to run the data, the CPU intervened and said you can't do that, and actually shut the application down. So again, that requires CPU usage, but the OS does support it as well. And finally, we have heap checking. So we have a lot of link checking in the heap now. We have cookies in the heap as well. These are all enabled by default. At its most simplistic level, when a heap block is about to be freed, Windows will look at the backward link of the forward link and the forward link of the backward link. And if both of those equal the current block, then we free the memory. If either of those three values is wrong, then something corrupted the heap, and we just leak that memory. There is actually a flag setting in Windows Vista where we will crash the app, and we'll do that for system components. One thing I want to point out about all these three defenses is they are just that, they're defenses. If you still have buffer overruns in your code, you still have buffer overruns in your code. This does not solve buffer overruns. The goal of these three defenses is to take some potentially exploitable buffer overruns where the bad guy can run code and turn them into a DOS. And again, that's still bad, but it's not as bad as running malicious code. Next, tools, Prefast and Sal. I'll talk about those in a moment. Well, actually, I'll talk about Sal in a moment. But Prefast is built now into Visual Studio 2005, and it is a static analysis tool where it can actually say, if these conditions are true, you have a buffer overrun in this code. And so it's a great way of finding bugs at compile time. And Sal is the standard annotation language which we can add to function prototypes to help Prefast find other bugs. And I'll give you, again, another example of that in a moment. And finally, just realizing you can do all this stuff and bugs can still elude you. You can, you're human beings, we're human beings, people make mistakes. Most importantly, the security research continues to evolve after you ship your product. Therefore, there are bug types that you may not even know about yet. And reducing attack surface reduces the severity. So a good example of that is the buffer overrun that led to the Zotob worm. I mean, that coding defect we missed. It was in Windows XP Service Pack 2. Yet, Windows XP Service Pack 2 users were protected from Zotob for two reasons, two defenses. One, the firewall is on by default. Let's assume you turn the firewall off. Well, Windows XP Service Pack 2 also requires authenticated RPC, remote procedure calls. So that prevented Zotob from exploiting the vulnerability as well. So I'm a great believer in reducing attack surface because no matter how hard you try, you will never get the code 100% correct. So I want to talk real briefly about the standard annotation language, SAL. SAL defines interface contracts between a caller and a callee. What's really cool is that Visual Studio 2005 supports this. Prefast understands it in Visual Studio 2005. And what's really, really cool is that we've annotated the Platform SDK headers and the Visual Studio 2005 headers so you can get all the benefit from the SAL annotations. So let me give you a real good example. Let's say you have a function splat, and let's say splat takes two arguments, a D word and a function and a pointer. And you know that that pointer points to data that is D word bytes in size because it says so in MSDN. Well, the compiler has no idea whatsoever. No idea. All it knows is there's a D word and a pointer, and that's it. Well, with SAL, you can actually say that this pointer is that many D words in size. Well, it's pointing to data there's this many D words in size. So you're linking those two arguments at the hip. And this really helps the tool find more bugs. So here are a couple of examples lifted straight out of the Visual C++ C runtime library. And just looking at one example, the call to fgets, you'll see that we've annotated the first buffer, char buff, with out ecount z max count. What that means is that that is an outbound null terminated buffer, and it must be at most max count elements in size. Now, prefast can run on your code and say, well, actually, if these conditions are true, that thing's will not be null terminated. Or if these conditions are true, you're saying that copy no more than 50, that this thing's 50 bytes in size, but you're copying it to a 30 byte buffer. You've got a buffer overrun here. So this really helps find harder to find bugs in the code, and more importantly, chances are very good that if prefast finds a bug relating to sal, a sal annotated function, then it's a real bug and not noise. Another defense is protecting pointers. This is if you've got a long-lived pointer, then you can use these functions that are built into Windows Server 2003 SP1 and Windows XP Service Pack 2 and beyond. And they're encode pointer, decode pointer, encode system pointer, and decode system pointer. So if you have a long-lived function pointer, then think about encoding it. All it does is it exclusive ORs the function pointer with a random number, and that's all it does. Now, what happens if the bad guy if there's a buffer overrun in your code and the bad guy overruns the function pointer, then when that value is decoded, it must actually decode to a valid pointer, which is actually not impossible, but pretty hard to pull off. So this raises the bar on the attackers. Again, this doesn't solve the problem. You should really be fixing your buffer overruns, but this is another defense. So if you have a long-lived pointer, you should use encode pointer, decode pointer, which are tied to the application, or encode system pointer and decode system pointer, which are tied to the box. So if you're passing pointers between processes, you'll need to use encode and decode system pointer. Other remedies for integer arithmetic: any calculation that's used to determine an array offset or a memory allocation size should be analyzed. Again, it's really important to understand what the bad guy controls here. If the bad guy controls one of the values that's used in that array offset or in that memory allocation, you've got a security bug, an integer overflow problem. Be wary again of unsigned versus signed mismatches. If you're doing array indexes and buffer sizes or calculating these things, use unsigned variables. Don't use signed variables. It makes no sense, because what does it mean to allocate -1 bytes? And watch out for certain warnings, because some of these warnings were just warnings in the past, but they now may be indicative of integer arithmetic problems. So watch out for these warnings. And most importantly, look out for pragmas and casts that shut the compiler up, because they may actually be masking real vulnerabilities in the code. From a coding perspective, if you have this classic pattern here, where you're allocating a number of things of size of t, you want to allocate a number of these things, and the bad guy controls or could potentially control the number of things to allocate, this is a bad pattern. So the way you can fix this is, one, is to do the reciprocal calculation. So you can actually say, okay, here's the calculation that calculates the how much memory to allocate. Here's the reciprocal calculation. If they don't match each other, then there was an overflow. And this example here is saying I only want to allocate 4 megs worth of thingies. Well, I really don't like this, because if the calculation becomes arbitrarily complex, then the reciprocal calculation becomes complex too. And we've seen people make mistakes in the reciprocal calculation. So personally, I'm not a big fan of doing the reciprocal calculation. Another example is, this is the reciprocal calculation. The first one is to restrict the number of things. So I've already talked about the reciprocal calculation. Next, actually the funny thing is the CPU knows there's been an overflow. Either the carry flag or the overflow flag on Intel CPUs is set. So what I wrote was some inline assembly language that actually checked that flag value. As much as it pains me to say this, I actually wouldn't recommend it that much, because it means adding inline assembly language to the code. The problem with that is, one, it's not portable. Two, it actually hinders the optimization of the backend compiler, because the compiler has not produced the code, so the optimizer can't make assumptions about that code. So personally, I actually wouldn't use this. My good friend and co-author David LeBlanc wrote a C++ template class called SafeInt, which is actually very, very cool. It's actually extremely fast too, which will actually do the calculations securely for you and safely for you. And in fact, the arithmetic that you do is just normal arithmetic. Once you just use these template classes instead, and the arithmetic is very, very natural. I would highly recommend this for C++ code. If you're writing just C code, there's a thing that we have in Windows called intsafe.h. The link to it is actually in the speaker notes for this slide, and these are just an array of functions that you can call in C or C++ for that matter that will do the safe arithmetic for you. Something else to also watch out for is calling new. The new operator actually has an overflow potential. Again, if the bad guy controls the number of things to allocate, that is really a multiply going on there. The number of things multiplied by the size of a thingy. Well, that could overflow. The cool thing is that Visual Studio, Visual C++ 2005 will catch this condition automatically at runtime. So a quick checklist for buffer overruns. Just fix them. If you have a buffer overrun in the code, don't argue about whether it's exploitable or not. Just fix them. Use defensive layers like the GS flag. Use the latest versions of Visual C++ or whatever compiler you're using, and make sure you're using the defenses that the compiler offers. In fact, to be honest with you, I would personally move off one compiler to another if the compiler doesn't offer very good defenses to the generated code. Use safer string handling libraries like safecrt or like stirsafe and so on. Use prefast and sal regularly. In fact, you must use sal at Microsoft for any buffer, any function that takes a writable buffer. And finally, review all arithmetic that's used to calculate an array offset or a memory allocation. So that's probably the biggest single section, and I now want to move on to other input trust problems. The first one is canonicalization issues. This is where you make a security decision based on the name of something. The problem is there's usually more than one way of naming something. Here's a good example. If your name is, you're this user account, domain/Mike, and you're trying to access secretfile.txt, then go away. Well, the problem is there's probably more than one way of naming secretfile.txt. And in fact, in Windows and in Linux and Unix and Mac OS X, there are multiple ways of naming things. But in a Windows example, you have secretfile.txt, could be secretfile.txt dot. It could be the auto-generated 8.3 file name. It could be the default data stream in an NTFS file. These are all examples of the same file, but with different names. Another example that's from that previous slide, he's just saying if the user is domain/Mike, then go away. Well, in Windows, I could use my UPN name, which could be Mike at domain.microsoft.com, for example. It's still me, just with a different name. So be very, very wary of making a trust decision based on the name of something. Another example is that sometimes these files are not really files at all. They're actually devices. And these devices exist in many, many products, many OSs like Windows and Linux and other Unix-based operating systems. For example, here I can open up a file called PRN. Oh, it's actually the default printer. It's not a file. And also be very wary that aux.asp, for example, aux.txt is actually still the default COM port. It is not actually an ASP file or a text file. Some other input trust issues, cross-site scripting. It's a web-specific issue. It's been around for a long time. It's very, very common vulnerability. And the flaw here is that the web server leads to potentially compromised data for the client. There's actually a variant of the attack, and I'll show that as well. But the fault here is that the web server trusts some input, then echoes the input back out without checking that the data is well formed. Here's a classic cross-site scripting bug, cookie stealing. Let's say you have a website called insecuresite.com, and it has a web page called welcome.asp, where it says hello, and then whatever was in the query string. Well, the bad guy controls whatever is ever in the query string. Remember, it's always important to understand what the bad guy controls. So in this case, the bad guy controls the query string. So what happens is the bad guy sends an email to Alice, for example, says, hey, click here to win $1 million. I mean, who's not going to click on that link? So Alice clicks on the link. If you look deeper inside the email message, you'll see that the link is actually an href to insecuresite.com, welcome.asp, name equals some script. And the script actually does a document.write and writes into Alice's browser image source, where the image comes from gotcha.com, but it also takes the cookie value and passes that cookie value to gotcha.com. So Alice ends up seeing hello and then a broken image icon, but more importantly, the bad guy who owns gotcha.com ends up getting Alice's cookie. Now you may think, well, so what? Well, imagine if there's something sensitive in the cookie, like a password or a username or some kind of credential. I mean, now the bad guy has the credential. The other attack is website defacement, but it's not really defacement. It appears to be defacement because that's what the user sees. So you've got to realize that any time code runs in a web page, that code can access the document's object model for that web page and change anything. So let's assume for a minute that msnbc.msn.com has a cross-site scripting bug. It doesn't, but let's assume it does for a minute. And you'll see at the top, there is location is Bellevue, Washington, and you'll see down the bottom, it has the weather for Bellevue, Washington, which, as per normal, is raining. So let's assume for a minute that that data is not sanitized. It just takes whatever's on the query string, just echoes it directly out to the browser. Let's also assume for a minute that this headline image, the front page headline here, is image number 4 in the DOM. The bad guy gets you to click on a link where location is not Bellevue, Washington or whatever. It's actually location is script document image number 4 dot source comes from badsite.com news.jpg. So we're changing the DOM at runtime. So the user clicks on this link. The user ends up seeing some gobbledygook in the address bar, which doesn't really matter because it's still, as you can see, it is still from MSNBC. But what's really interesting is there is no place called script document images number 4 source equals blah blah blah. There is no such place. So as you can see down the bottom, there is actually no weather at a place called whatever that place is. But what's really interesting is the headlines change. And it changes from being whatever the normal headlines were to something that's a little bit more interesting. And who knows, perhaps enough people read that headline to actually believe that the Dow did actually plunge 3,000 points or is plunging 3,000 points and dump their stock, and it becomes a self-fulfilling prophecy. Who knows? Again, the attack here may be a little bit more subtle. You could change all the links to point to hate sites or porn sites or something. I mean, you could change anything you wanted in the DOM, all because you didn't scrub data before presenting it back in the browser. Another kind of input trust issue, and I am going to come on to mitigations in a minute. I'm not just whining about these bugs, and we'll show you mitigations in a moment. And this is the SQL injection attack. Of all the issue types, SQL injection attacks kind of worry me the most. Yeah, buffer overruns are obviously a big concern, but SQL injection attacks are a big concern for a number of reasons. One, they can give you the crown jewels. I'll give you examples of that in a minute. Two, they're written in what people often view as safe languages, C#, okay, generally considered a safe runtime language. Well, here's a SQL injection vulnerability written in C#. This could be Java, it could be JSP, it could be Perl, it could be PHP, it could be Python. And also, a lot of websites, a lot of line of business apps talk to databases. And people write code like this every single day. And if you've got code like this, I could get to the back-end data and actually read anything I wanted. And again, I'm going to give you an example of all this in a minute. There's a bunch of bugs in this code. One, there's an embedded password in the code, which is a really lousy password too. We're connecting as the sysadmin, the SA account, and I'll explain why all this is bad shortly. We're using string concatenation to build up dynamic SQL. And finally, if anything goes wrong, we tell the bad guy exactly what failed. And I'm going to explain why all of these are bad. So why it's wrong? Why all this code is wrong? Again, it's always really important to understand what the bad guy controls. In this case, the bad guy controls the shipping ID. So a good guy will go up to the website and type in his shipping ID of 1001 into the web page, and the back end would then build up the SQL statement using this code at the top. And we'll build up this SQL statement, which is select has shipped from shipment where ID equals 1001. And the yellow part is what the bad guy entered. Well, if it's shipped, excellent. If it hasn't shipped, it tells you that it hasn't shipped. No problem. Not so nice guys do something like this. They type in a shipping ID of 1001 single quote, or 2 is greater than 1 dash dash. So what that does is changes the semantics of the SQL query. Now remember very early on I said remember 1 equals 1, but not for the reasons you think. So the question I want to ask you is, why did I do 2 is greater than, or 2 is greater than 1 here? Now the reason why I did 2 is greater than 1 is because the condition 2 is greater than 1 is always true. So this gives me all the shipping information, everyone's shipping status. And they may think, well, okay, that's hardly exciting. But imagine if this was select credit card information from customer, where credit card number equals blah, 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 or 2 is greater than 1. Now that is a very interesting attack. So, but I still haven't answered my question. Why did I do 2 is greater than 1 when I told you to remember 1 equals 1? And the reason is, you'd be amazed how many people have their intrusion detection systems primed to watch for 1 equals 1. I'm not going to use 1 equals 1. I'm going to use something else that's also true that you may not be looking for, which is 2 is greater than 1 in this case. I had one person tell me once in a presentation that I was trying to redirect standard error. I think that person had been using the bash shell for too long. And then next is dash dash. The dash dash operator comments out that final single quote. If you look at the SQL statement at the very top of this slide, you'll see that there's actually a single quote at the very end. That the bad guy does not control that. It's actually in the code. So the dash dash operator comments it out. And the bad guy actually closes off the single quote after 1001. So it's really important that you understand what the comment operators are for the database that you use. Not really bad guys, they go and then delete the orders table. Well, okay, that's kind of bad. And then really rotten people actually go and add themselves to the admin group by calling XP_command shell, which is built into SQL Server, and they call net user add, and then they add themselves to the backend database. Actually, they add them to the backend computer, actually. Maybe you're thinking, well, hang on a minute. How do you know there's an orders table? You drop table orders. I mean, do you take one of the monkeys off the works of Shakespeare for a minute to get them to just go and randomly do work out order tables that are in the database? No. Some people often say, well, there's always an orders table. Yeah, perhaps. But there's a better way you can do it, and that is to actually get the data from the database. Realize a database is self-describing. There's a table in the database that this explains all the objects in the database. So, for example, in the case of SQL Server, there's a table called sysobjects. So I could do select star from sysobjects where X type equals U. And it will give me a list of all the user-defined tables in the database. And there is, there's the orders table. Someone once said to me, well, perhaps it's in the error message. I've yet to see an error message that says, no, there's no such thing as the orders table. Did you mean one of these tables? I've yet to see an error message like that. The next thing is, well, okay, hang on a minute. How can you go and delete the orders table? How can you run XP_command shell? You've got to be the sysadmin to do that. Go back and look at the code. We're connecting as SA, the sysadmin account. Do you need to be sysadmin to query the shipment table? No. I mean, what principle does that violate? Go back to Sean's discussion about design principles. It violates the principle of least privilege. Do you need to be sys-A to query the shipment table? No. Do you need to be SA to compromise SQL Server? Yep. Do you need to be after you compromise SQL Server, could you potentially take out the box? Yep. Once taken out the box, could you potentially start taking out the network? Yep. Which leads you to your worst nightmare. And this is a slide that I built from a scenario by a colleague of mine, Jesper Johansson. So let me explain the scenario. Here we have a backend database, and we have a firewall in the middle, and we have a computer that's owned, spelt with a 0. It's owned by a bad guy. I say owned with a 0, meaning this is a computer that's under the control of a bad guy on the internet. This is not something that Jesper went out and actually bought, CompUSA, for example. There's a firewall in the way. Frankly, you may as well throw the firewall away. And the reason for that is because this is probably a web front end to a backend SQL database, and you're going to allow port 80 traffic through the firewall. So, in fact, we're so cynical in our group, we don't even call HTTP anymore. We call it UFTP, the Universal Firewall Traversal Protocol, which is exactly what it is. So, let me get back to the story. So, first of all, there's a backend, there's a SQL injection attack at the backend database. and the attacker executes this command. And what he does is call tftp.exe to pull down netcat from the other compromised machine onto the machine that's about to be compromised, the SQL Server machine. Netcat is a very well-known tool. It can work in many, many ways. You can run as a client or as a server. And it can also work in such a way that when it connects to something else, it can spin up another process and actually bind standard in, standard out, and standard error to a socket. And you'll see why that's an interesting attack in a moment. So now I've got netcat on the SQL Server machine, but it's latent, it's doing nothing. Then I spin up another version of netcat on the other machine that I currently control, and it's in listening mode. In this case, I'm listening on port 31337. Then I do another SQL injection attack at the backend SQL database again, and I call the netcat that was latent. By the way, I'm probably not going to call it netcat.exe on the other machine. I'm going to call it probably virus checker or something. So I then run netcat again, and I run it in such a way that it connects to the other machine that was listening on port 31337, but in doing so, it spins up a command.exe shell and binds standard in, standard out, and standard error of that command shell to that socket. So now the bad guy has a shell on the machine that's actually a shell on the remote machine. Anything he types in this shell is actually happening on the other machine. And if the process that was compromised is running a system context, that shell is running a system context too. At that point, the bad guy can completely compromise the box, totally compromise the box. And that was all because of the application of had a SQL injection attack, and the ports were open, obviously, and it's running an elevated privilege. At that point, it's game over. The attacker can do anything he or she wants on the box. Another interesting attack, and there's another interesting input trust issue, is called the Turkish eye problem that also applies to Azerbaijan. Unlike English, which has two-letter I's, we have a lowercase I with a dot and an uppercase I with no dot. Turkish actually has four-letter I's. The ones with a dot are pronounced I, and the ones without a dot are pronounced U, with apologies to those who understand the Turkish language. But if you take a lowercase I in the Turkish locale and you uppercase it, you actually don't get what we would normally expect. You would get an uppercase I with a dot on the top, as you can see here. So where's the security bug? Imagine if you had code like this running in the Turkish locale. It says, don't allow file monikers, don't allow file colon whack whack whack, when you're using a URL. So what you do here is take a URL and you uppercase it. And if it equals the word file, then go away. Well, in the Turkish locale, you don't get F-I-L-E colon. You get F-I with a dot on the top, L-E colon, which is not what you're expecting. The badness that you don't want is this word file colon. Well, in the Turkish locale, if I do a lowercase file, you don't get that. And so I can possibly get past your security check. Another good example of not relying on a name to make a security decision. The correct way of doing it is to do a culture invariant uppercase and look for what you expect to be good. In this case, I'm only going to allow HTTP requests. Another guy in our group actually said that's an okay defense, but it's still not the best. The best defense is to actually call the URL cracker library that's built into the .NET framework and say, what protocol is this? Make it in a single location as opposed to spread out all over the code. So how do you remedy these input trust problems? Well, the first one is to validate all input, right? I mean, if someone gives you stuff, just treat it as being evil until proven otherwise. And look for valid data. Don't look for good stuff. Don't look for bad stuff. Look for what you expect, and if you don't see what you expect, then reject the data. For cross-site scripting specific issues, again, validate all input. Never directly echo web-based input. If you get something in a query string or in a form, don't just blindly echo it back out again. That's how you get cross-site scripting bugs. At the very least, HTML encode the output. ASP.NET 1.1 adds a thing called the validate request option. It is enabled by default. It is a defense. It does not solve cross-site scripting bugs. What it does is if ASP.NET detects what looks like script or HTML in, say, a query string, it just rejects the request. Now, again, this is a defense. It doesn't fix the problem. Do not rely on this. Say, well, we're going to have cross-site scripting bugs all over our code as long as we enable this. Not true. Make sure there's no cross-site scripting bugs in your code, and enable this, which, by the way, is enabled by default. For IE6 Service Pack 1, we added a thing called the HTTP only cookie. So you can actually mark a cookie with semicolon HTTP only. And then if you do have a cross-site scripting bug and someone tries to call document.cookie, the browser will only give them back a blank string. They will not see the actual cookie. And finally, you can use in a frame set, you can actually say that frame element runs in is untrusted, which means that script will not run, IE will enforce that. For SQL injection, guess what? Validate all input. Again, use parameterized queries. Don't use string concatenation. And finally, for hyper-secure environments, consider allowing access only to the stored procedures and denying access to the underlying tables. And that way, if the user can, in some way, or the attacker can bust out of the stored procedure in some way, for example, there's a SQL injection attack in the stored procedure, then they can't query the table directly necessarily. So deny access to the underlying database objects and allow access only through the stored procedures. And again, I've already alluded to this, but use parameterized queries, and the most secure way is to use parameterized queries with stored procedures. That is by far the most secure way. And I want to stress this is really important. Don't look only for bad things. It assumes you know all the bad things. Like, don't go looking for this bad word or this bad construct, because there may be a variant of that construct that you don't know about yet. So here's an article that came a couple of years ago in Linux Journal on how to write secure PHP code. And the example the author gave, which is advice I would never follow, is this is how to filter out harmful SQL commands. It's wrong on many, many levels. One is, well, delete, update, union, and insert hardly represent the complete SQL grammar. That's number one. Two, they're looking for bad things that they don't want. And third, delete. Some databases use drop. Don't use delete. Again, it's another example of a different word that's being used to represent an action. So don't do that. The other problem with this code is that it looks for these bad things, then replaces them with a blank. I can get the word delete through this code in plain sight. I'm not using any kind of stupid little tricks. And the secret is to put the word delete inside the word delete. So this code will strip out the end of delete, and I'm left with delete. Got straight through this code. So don't look only for bad things. It assumes you know all the bad things. So the input error checklist, if you just drill into your head, it's just one thing, and that is that all input is evil. If you understand that, then a lot of the major bugs just go away. And again, don't look only for the bad things. Look for the good things. I'm not saying don't look for bad things at all. Look at the sentence. It says don't look only for bad things. If you're looking for bad things, make sure you're looking for good things too, and filter primarily on the good things. So that was the biggest section by far, the input trust stuff. So now I want to move on to the sort of everything else category, which is still important, but and must be looked at. The first one is storing secrets. You've got to realize that software cannot defend itself. If a user has unbridled access to a device with software on it, then they can get any secret that is maintained by that device. Embedded secrets don't stay secret for very long whatsoever. That same article on how to write secure PHP code actually told how to do crypto. The problem is they had an embedded key. You do not embed keys in code. You cannot embed keys in code because they will be discovered very, very easily. What's even worse about this example is the entropy for the key is really lousy too. It's not exactly random. The recommendation on the Windows platform is to use the data protection API. There's only really two functions you need to worry about, crypt-protect and crypt-unprotect data. There are managed wrappers available pre-Visual Studio 2005, and Visual Studio 2005 adds the protected data class as well. All supported platforms, Windows platforms support DP API, and it's much more preferable to LSA secrets. LSA secrets was a way that we had in Windows for storing sensitive data. We want people to move away from using that. Rather, they should use the data protection API. Don't go building your own crypto. Weak crypto, aka encryption, is not the way to go. You should be using the libraries that are available to you, like Crypto API for C and C++ code. On Windows Vista, we have a thing called CNG, which is also accessible to C and C++ code. For script, we have Capicom. So if you're writing ASP code or VB script code or JavaScript code and so on, then think about using Capicom. Capicom is just a wrapper around Crypto API. The cool thing about Capicom is the developers did a stunningly good job of creating a very simple, very robust, and easy to use set of objects and methods for doing encryption, digital signatures, random number generation, etc. I would highly recommend you look at Capicom. And finally, for managed code, you should be using the system.security.cryptography namespace. For SDL, we have banned the use of certain functions, certain algorithms. So MD4, MD5 are banned completely for new code, as is SHA-1. RC4 is banned because it's a stream cipher and people make a lot of mistakes in the way they call stream ciphers. I'm not going to go into all the gory details right now. They're documented in Running Secure Code 2nd edition. But essentially, if you need to use RC4 for whatever reason at Microsoft, you must get the way you're using it reviewed by a cryptographer. DES is banned because the key size is just too small. 56-bit key is just not good enough for today's standards. Of course, there are maybe backward compatibility issues here. So, for example, digest authentication has to use MD5. There's no notion of crypto agility. You can't upgrade digest to use another hash algorithm, for example. So we have to use MD5. For symmetric algorithms, we're recommending or requiring for new code AES, and for digest, we're recommending and requiring SHA-256 or better. And symmetric keys must be greater than or equal to 128 bits. There are some managed code specific issues that you need to be aware of. First of all, got to get over this hurdle. Because you have code access security does not mean your code is secure. I already given you two examples. One was calling unmanaged C++ code from C#. The other example was calling, doing SQL statements and building up SQL queries from C#. Code access security is there, but it didn't save you. So don't think because you have CAS, you have secure code. It's absolutely not true whatsoever. There are the secure coding guidelines on MSDN. I heartily recommend you read them. Be wary of granting certain permissions to your code. If you're familiar with privileges in Windows, there are some privileges in Windows that we're always very, very leery of, like the TCB privilege, which is the trusted computing-based privilege, the backup privilege, debug privilege, restore privilege, load device driver privilege. These are all very dangerous privileges in Windows that you grant very, very carefully to certain accounts. And it's the same with certain kinds of permissions in .NET code. And finally, you should be running FXCOP regularly, looking for issues in code. In Visual Studio 2005, you can make it part of the build process. FXCOP is actually built into the application. There are some things that we always look at very carefully when we're auditing .NET code. One is the link demand. So normally what happens, actually, you know what? I'll show you a picture instead. Normally, when code calls your code, and your code does implements some read file thing, so you're reading files from the file system. Normally what you would do is demand that all the callers have a thing called the file I/O permission. And if any of the callers do not have that permission, this fails. And an exception is raised. The link demand is different. The link demand is only done once, and it's done at JIT when the code is just in time compiled. It's done once, and it's only done against the immediate caller. A full demand, which is what this is, optimizations aside, this demand is checked on every single call, optimizations aside. A link demand is an optimization, where code calls your code, but what you do is you do a link demand for the file I/O permission, which means that only the immediate caller is verified. Make sure they have the appropriate permission. The problem here is if the bad guy can lure the code that calls your code into doing his bidding, he doesn't need the file I/O permission. So our little rule of thumb at Microsoft is that unless you're in the .NET Framework team, you shouldn't be calling link demand. And every time you do, these will get audited, and we look at these luring attacks. Next is partial trust. We have this thing called the allow partially trusted callers attribute, which allows code that comes essentially from the internet, partially trusted code, to call your code. Is that what you want? If your code is very complex, has a lot of functionality, do you really want code that comes from the internet to call your code? And if the answer is yes, then that code better be very, very secure. If the answer is no, then you should not have the allow partially trusted callers attribute set on the code. And Managed C++ and APTCA, we reviewed that extensively. We thoroughly review any code that is written in Managed C++ and has this capability enabled. Asserts, something else we look at. This is not the same as a C or C++ assert where you're asserting that some condition is true. This is quite different. This is asserting that you're going to use a permission safely. So let me give you some examples. Let's say you have this example again. Code calls your code, and you implement this read file thing, and all the callers are verified to make sure that you have the file IO permission. Well, what happens if your implementation of read file is extremely constrained? You do like one little thing on one little file. Do the callers have to have the file IO permission? The answer is possibly not. So code calls your code. You assert the file IO permission. At that point, the stack walk stops. The rest of the callers are not checked. Now, let me give you an example of a safe example and then an insecure example. Here's an example where we're asserting that we're going to manipulate this one file. What does the bad guy control here? Absolutely nothing. This is probably very secure. Now compare it to this, where you're asserting the file IO permission again, but the bad guy controls the log file name. This is absolutely insecure. This is not a good use of security assertions, and this code should be eradicated. Watch out for calls to platform invoke and com interop. These are your gateways to buffer overruns. Remember, a lot of these platform invokes and com interops, you may be calling out, in fact you probably are calling out to unmanaged C or C++. And that's probably where your buffer overruns are going to lie. So be very, very wary of all these platform invokes and com interop calls. Also watch out for read-only. Read-only isn't really read-only. It is, but there's some little subtle semantics you should be aware of. Here we have an example of a read-only array of bytes of valid key sizes. The array is read-only. The elements are not, which means that I may be able to change the elements in the array. Imagine if I could change all the elements in the array here to all be the number 8. That means if I go and ask the .NET Framework to say, hey, give me a list of all the valid, the strongest key size you have, it will give me the number 8 back, an 8-bit key. That's it. So be aware that the array is read-only, but the elements are not, and watch out for that. And also watch out for integer arithmetic problems in managed code. These affect Java as well. Here you have an example where you're getting a number from the network, a 16-bit signed integer. Again, it comes from the network, so the bad guy probably controls this. And you're saying if the number is less than max, then we're okay. Well, what happens if that value is -1? You add 1 to the result, and then you divide 8k by 0. Whammo. Your app just crashed with a divide by 0. Well, what about this example? Again, you're reading a 16-bit signed integer off the network. And as you get a request off the network, you add that request and some other metadata to an array. Well, what happens if the incoming requests are at a higher speed than the data you're taking out of the array? In this case, you may actually wrap around at 32k and try to access element number negative 32,767, blah, blah, blah. Well, at that point, there is no such thing as element array, negative 32,000. And the app just crashes with an array bounds exception. So these are actually very real bugs that could affect high-level languages, not C and C++. They're not buffer overflows, but they can still cause your app to crash, which is this would be really bad if this was a server. So some other resources, Writing Secure Code, 2nd edition, written by David LeBlanc and myself, still selling very well. 19 Deadly Sins of Software Security, written by David and I, and an open source software developer by the name of John Viega, who works at McAfee. This is a very small book relative to Writing Secure Code. We focused on the 19 top issues. So, for example, buffer overflows, integer overflows, SQL injection attacks, cross-site scripting, crypto issues, and so on. And these 19 issues really accommodate for upwards of 90% of the bugs that we see on the internet. And we made it essentially language agnostic, except some specific to languages, obviously. But we also look at different platforms, different databases, different web servers, different development environments, and so on. So this is actually a very holistic book looking across the whole industry, not just Microsoft platforms and not just, say, the Linux or Unix platform. Threat modeling book by Frank and Window. The .NET Framework Security book is still probably the best book on the subject. These guys, Brian Lamarcki and Matt Lyons and Sebastian Lang, all work at Microsoft and have worked on the .NET Framework team. How to Break Software Security by Whitaker and Thompson. It's very client-centric, but it's a very good book for understanding how you can actually compromise the client's environment. Next is Improving Web Application Security by the Practices and Patterns people at Microsoft. This is one of my favorite books because it looks at how you build software from the correct perspective, which is look at the threats and how you can mitigate those threats, which is exactly the way you should think about building secure systems. Next one is if you're building or want to understand more about crypto from a very pragmatic perspective, the book Practical Cryptography by Ferguson and Schneier. Niels Ferguson works at Microsoft. He works in the Windows security team. An incredibly pragmatic book. It's a very, very easy read. It's one of the few crypto books where you can actually read it end to end and actually understand it. And finally, Grey Hat Hacking. One of the authors is Jonathan Ness. He works in our group. And this is a really cool book for understanding how bad guys really will attempt to compromise your software. It's a very, very good read. I highly recommend all of these books. So in summary of the entire presentation, we gave a very simple, Steve gave a very straightforward introduction to the goals of trustworthy computing. We then moved on to Eric talking about the SDL at a very high-level view, which is the whole point of this book. Sean then talked about pragmatic security design. I mean, we could talk about the theories of the security design, but we figure you have a job to do, so we thought we'd hit the most important points. I then talked about a brief introduction to threat modeling, which is explained in Chapter 9 of the book under risk analysis. Sean then talked about security testing, again, a very high-level view of testing. And finally, I wrapped it up with secure coding issues. We hope you enjoy reading the rest of this book. I know Steve and I have had a great deal of fun writing the book. The book would not have been made possible without the help of so many people, both within Microsoft and within the SDL and the SWI teams. And also a lot of people outside of Microsoft gave us a lot of feedback on this book. And we hope that the book really helps you in changing your processes to deliver more secure software. And we know that Microsoft, that we've seen great benefit in implementing SDL. Most notably, that benefit is for you, our customers, the people who are using our software.